So this is part 2 of a video about affineness of jet spaces of curves with non-trivial Kodaira-Spencer class. And again, so we're working over a function field, and we're going to have a derivation on the function field. What I wanted to show is I wanted to show that this thing was affine by showing that the torsor was really so the jet space is a torsor under the tangent bundle, and local sections of the jet space are lifts of the derivative on the base over the coordinate ring of whatever over the coordinate ring of the thing you're taking the open set you're taking a local section over. And okay, so now I'm kind of going to give an abstract presentation of the torsor as a projective bundle minus d. So a certain divisor, a certain ample divisor. So we're going to kind of give it an abstract setup now. And so let J, so this is going to stand for the jet space, be a torsor defined by, let's say with the class of J, and we'll call this eta. So this is a class of the torsor, and torsors are classified by H1. And now we need to do something. So this is going to be, so F here is going to be a vector bundle on X. And hold on one second. My voice is kind of going out. And so this is going to be the something under the dual of this. So you should think of this as being the cotangent sheaf and this being the tangent sheaf in our application. And this is just a class associated to the torsor. Okay, so we're going to do this. It has, so there's a canonical projection. By the way, there exists a canonical projection from X to J, or sorry, from J to X. So this is going to be a torsor over X. X is going to be a scheme. And I kind of want to just give an alternative construction. We will give a construction just based on from the cohomology class. From the cohomology class. Okay, so here's what we do. So we're going to take a covering. So these are going to be affine open covering. This is a covering of schemes, and then we're going to take some presentation of these guys. So xi intersect xj of f here. So these are going to be representing this class eta. So we're going to take some cocycle representing the class. And now I'm using this, we have the following fact. So the fact of life is that J is going to be equal to a bunch of gluings of the symmetric algebra of F of, so we take these global sections here over these open sets. And so I need to explain this gluing. So here we're going to take automorphisms of S of F of. Okay, so this is the symmetric algebra here. We need to define the automorphism of the symmetric algebra, and phi ij of some element of F is going to be equal to F plus, and then we take eta ij and we pair it. So v eta ij here. So and this goes for F and F. Okay, so this is the pairing between F and F dual. So this eta here, these eta IGs are at F dual, and then these guys are going to be in F, and this is the transition between the two things. So if you're going to actually use this in practice, you have to be careful, really careful with your sign conventions, because when you switch, this has happened to me before, if you switch i's and j's and i's, you can land up in a dual, and duals tend to have very different cohomology. And so if you're doing a computation that relies on check cohomology, you really need to be careful about these things. So, and I haven't been so careful doing this, but so I just double check everything if you plan to use this ever. Also, okay, so this is one version of the presentation of this, and the fact that this is a torsor is maybe. Well, I'll show you another presentation where it's clear that this is a torsor. So this is the first presentation, the first construction of J from the cohomology classes. I want to give an alternative construction, but first I need to kind of construct E first. Okay, so I'm gonna do this projective bundle construction that we talked about in the first video. But first I need to do what E is. So so let me give a construction of E. So again, so we're going to fix eta ij in, and I'm going to write this a different way, xi intersect xj. So this is the same thing as h0 that I wrote before. Let's remember that this f thing, this is a HOM. So this is a morphism of O of x modules here, from this guy to this guy. So we need to consider now that we saw that eta gives rise to an extension here of O of x E F O, and we have this S here, and this is the extension associated to eta in. So this is an H1 of x F duals. This is what we started with. This is the particular class, and this is isomorphic to the extensions of E by O of x, like so. Okay, so the fact that I wanted to give is that E is isomorphic to a disjoint union of so these are going to be glued together of i's. So we have these gluings here, and now I need to explain the gluings. So this psi ij is going to be a transition here to, and so this is maybe E restricted to x. Sorry, this is F. F of xij. So these are kind of local. So locally, always locally, the sequence will split into a direct sum. This is an exact sequence of vector bundles, and I need to explain how this works. So we'll take a function f here and a vector here. So maybe it's bad that the f doesn't belong to the f, but whatever. So this guy maps to. So we take f plus eta ij of v. Okay. So this is what the transition maps looks like. It takes takes a little piece of this v and moves it over here using the fact that this is a dual. So it makes sense to apply eta ij to elements of v and get things in here. Okay, so we're going to use there's two presentations. So okay, so this is one presentation here. I want to give now. I want to give the second construction of second presentation of J. So second presentation. Let me explain what the first presentation was again. So the first presentation was where was it? This is the first presentation. So this is the first presentation. So it's a bunch of, so okay, again, this thing here, after we choose a basis, this thing just looks like affine space, okay, with coefficients in O of xi. And then this is the transitions between the two. You don't see the transition matrices for the vector bundle because they're hidden in the V here. Okay, I got to sneeze. 1 second. Okay, now okay, we constructed this thing here, and now we're going to do a second presentation of J, and the alternative description is the one that I was going to talk about. It's so it's the fact is that J is going to be isomorphic to P of E. So I haven't proved that the two things are the same. I'm just telling you what they are. That this is here. This is what this looks like. This is divisor associated to omega. F. So we're not doing omega in this case. And okay, so we have this presentation here, and this is going to rely on the fact another fact that says that that's a presentation of the projective bundle of E. So this thing, as we've said before, this is a proj of the symmetric algebra of E, and this thing is glued locally over open sets by taking projes of the symmetric algebra of E restricted to xi. And then we'll take some equivalence relation, and I need to say what this is, so it needs to be specified. But to specify this, I first need to say some more about the extension. Okay, so locally, we can look at this sequence here, E, F, 0, this is on X, this is a S. This is, the sequence is split. Okay, and we have a split sequence. Well, this means that E of X, E of, let's say, Xi has a basis. Let's say T0, Tn. So this is going to be rank n. This is going to be rank n vector bundle, and so what's going on here is that T0 is a generator. So the T0 generates the image here of S of O of X, and then T1 through Tn maps to basis of F, and in this case, we see that that the symmetric algebra. So again, we're going to look at this thing here. Okay, and if we've chosen it so that we have the sequences split, so locally this means over xi we have this splitting of modules. We're going to have that here S of E of xi. So this is the symmetric algebra of this thing. Looks like O of xi T0 Tn. So there's kind of an isomorphism this way. These are the basis things. So maybe I could put parentheses like this. Okay, so we'll take sections rather than viewing this as a sheaf. Okay, so it's just, I think, cleaner notation-wise. And then it's kind of clear to see that here, since this is going to be a generator of this, okay, so F is going to be the quotient of F is going to be the quotient of E by O of X, and that's going to amount to setting T this thing equal to 0. T0 is equal to 0. Okay, so this corresponds to D of xi, which is really a part of well, the proj of S of E of xi. So this is what's going to cut out. So this cuts out. This glues together to give, let's say, D, which is P of F. Okay. So now you can kind of see what these things are going to do. And now we claim the following. So there's the lemma. that I've kind of outlined or described, that J is isomorphic to D. This thing is going to be so here S of so let's say how do I want to do this? Well, I can write it like this: spec of S of E of xi. And then we're going to take a local splitting, and then we're going to invert t, let's say 0, and then this is going to depend on the ith guy here. Okay, so we have to do this for each I, so this is going to have coordinates t, our basis, so it depends on a splitting, and we take a splitting, and it's going to have t0 up through t capital N, and we're going to write a superscript I for that, just like here. So maybe here I should have written here a superscript i's everywhere. This doesn't mean derivative or anything. And this is going to give us the one piece of this divisor, which corresponds to the projective bundle here from this surjection. Okay, so we have this, and there's going to be some gluing here. And this is, by this equality here, I mean, this is from the first description, presentation. And I mean that this is the second presentation. So I wrote down two things. I didn't show that they were isomorphic. And I guess on this side, we had a bunch of, this side here was a disjoint union of S of, so what do we have? Specs of S of F of xi's, like this. And on this side we had this. This isomorphism, the isomorphism is induced by the isomorphisms of rings here, T0I, F of xi, like so. Okay, so we have these two isomorphisms here of these rings. Okay. Okay, so this is what I want to show, is I want to show that we have these two presentations. This is a torsor, this is a torsor. This one was glued. We got these by gluing together and doing a transition map like this here. And then this one, so the fact that I can switch between the subscripts and the parentheses comes from the fact that we have something that's quasi-coherent, so it's locally like a module. So f of xi is f sub xi is really f parentheses xi tilde. Okay, so that's how you switch between the two. Okay, and so then we gave this description here, and this one has to do with the fact that this guy here is glued together in oh wait, that has to do with this one, and then the other one, the first one was the round, this guy here. So this is the first presentation, and then this will deal with the second presentation, which depends on the construction of E. Okay, so yeah, so this is the second presentation here. Okay, let's put that there. And then we use the fact that we had the splitting. Okay, we have this here. Okay, great. Okay, so let's let me sketch the proof. Okay, so we'll take we'll have these isomorphisms of sheaves. So locally, so this is over xi. We're going to have E of xi is going to be isomorphic to O of xi direct sum F of xi, and this is going to be via the splitting. Let's say T0i up to Tn of I. like so. And so again, these last pieces are going to give the basis here. This one's going to give a basis here. And the transition maps, and so we have these transition maps. We have transitions. Where FV goes to F plus 8ijv, comma V. Okay, and so this is in E of xij, and this is in E of xij here. Okay, so we have this guy here. And so this is after really a trivialization. Okay, so let me explain the sheaf of splittings. So there's a sheaf of splittings. It says that, so we'll take E, F, 0. And if we take two splittings here, tau 1 and tau 2, these are splittings locally. So we'll suppose that this is over some xi. So these will be local sections. And exactness, so this... Okay, so from exactness, this tells us that if we subtract these two guys at some element, so here for V is going to be an F, this thing is going to look like, if this is S, it's going to be the image of some guy here. So there's, so for all these guys, there exists an F in here, such that this formula holds. Okay, and actually this tells us we have a map, which tells us that we can take T1 and T2, these splittings, pairs of local splittings, and we can map them to F. And this guy is defined to be equal to the inverse image, and this is actually going to be well defined, of tau 1 minus tau 2, like this. So we can take local splittings, and then we can take S inverse of these two guys here. Okay, then this is actually going to define an element of F dual, and so this gives, then let's make this definition, split of, let's say, the sequence the structure of a torsor. Torsor under this guy. Okay, so so here's our lemma. So the cocycle. Oh, and it. Okay, let me say, I guess, another fact. Split is represented by P of E, P of F. Okay, so I'm not going to do this fact, but so hence it's to show that as torsors, it's enough to show that split has the class as J in H1 of XF dual. Okay, so if this guy was built from eta, then this guy needs to be built from eta as well. Okay, so we're going to use this fact here that the splitting is represented by this thing. So this is something I need to do. Okay. So lemma. So the cocycle, so let tau I be elements of this splitting of here of xi. Okay, then it turns out that S inverse composed with tau I minus tau j of v is equal to eta ij of v. Let's say that, let's say here, homologous, or cohomologous. Okay, so here's the proof. So fix description of E. Okay, so we'll fix this description of E, and here's where we're going to use trivialization, phi I, as O of xi. So we fix these splittings here, and we're going to do it so that here under so we choose tau I, or we can say that we choose the trivialization. It depends on your, tomatoes, one of the way, so that the following works. So we have f of xi, we have the splitting, so this is f restricted to xi of e restricted to, or e restricted to xi, or e of xi piece, and then we take this trivialization, so this is the splitting where it's the direct sum. And what we do is this thing will take v, and it maps it to tau I of v. And after applying phi, we just want it to just get only the f piece here. Okay, so we take the splitting, and then we take the physical thing, and then we take this trivialization as a direct sum, and we want it to behave like so. And so what we can do is now we can consider what happens when we transition. Okay, so what we'll be able to do is we'll be able to take f of xi. It'll go to e of xi, so we have this splitting here, and we can go to O of xi tensor. So O of xi tensor f restricted to xi, and this is phi of I, and let's take it on the double intersection. And what we could do is we can consider, again, maybe f of xji. We could consider what happens when we transition. So this could be another trivialization. So these two guys are the same, and this could go into x of ji like so. And so what this thing will send is it'll send 0v, like we had this image here. This will map to eta ij v v. This uses where is it? This uses this part here, the presentation here. Okay, so then this f is going to be 0 here, and so what we just get is this extra piece here. Okay, so this is this transition map. Another way to say this is phi j. This is e of xij, like so. And so these, we wrote this ji. Okay, so there's kind of two trivializations here. These two things are equal. And so what this is saying is that this map here is really phi I inverse composed with phi j. Okay, so we have those two. That's nice. So now what we can do is we can also consider what happens when we take a v. So v could be in here, or it could be in here. And if we go this route, this goes to tau j here, and once we put that in here, so we'll get inside this thing, this will be phi j composed with tau j of v, and this is going to be 0v, because we've cooked up our trivializations to be this way. And so what does this tell us? So this tells us that, so when we take, so we can take the difference of these two things, so phi j composed with, let's say, tau I of v minus tau j of v. So we have these two things. So this is going to be equal to, here, phi j of, so now this is phi I tau, so this thing is tau I phi I of v. Okay, so this is so I want this to be equal to eta ij of v 0. Okay, so this thing here is phi j composed with tau I of tau I inverse tau I of or sorry, phi I of tau I of v, like this, minus phi j tau j of v. Okay, and this is equal to, so this is this transition map, and this one was, so this one was here, and so we transition, we get eta ij v minus 0v. Okay, when we subtract them, we get what we wanted. We get this thing here. Okay, so we get these two things. The difference of these two things is this. All right. Okay, so once we have this, we can actually now take S inverse. Okay, so now we actually don't need to apply this. We can actually see so we have this, again, we wanted to see what the Torsor thing looks like. And it turns out that this implies that S inverse of tau I minus tau j is equal to eta ij, like so. Okay, and so this thing here is actually, this is the cohomology class, so this tells us, this implies cl of this splitting of the sequence, sorry, O, E, F, O is equal to eta, which is really the class of by construction, of class of J. Okay, and that's it. And so I guess what we didn't show is that this thing was ample. Okay, so now we need to just so we just proved that splitting and splitting and the J are isomorphic, and it remains to show the ampleness. Okay, so how do we do the ampleness? So let me just say, how do we do the ampleness? The ampleness here, it follows from this description here. So so it's clear that this thing here, what we're doing is we're localizing at a hyperplane section. So from this description, we have that that D is in O PE 1. So this is this linear system series here. So again, D is cut out by this guy by this choice. This is really what we've really done is we've shifted everything over by 1, and in this grading, and then and since this is going to be ample by Gieseker's theorem, so this is going to be ample. And that's the theorem. Okay. Thanks for watching.